Imagine a place so deep that sunlight never arrives, so remote that only a handful of people have ever seen it, and so extreme that the pressure could crush a car like a soda can. That place is the Mariana Trench, a long crescent-shaped scar in the western Pacific, east of the Mariana Islands near Guam. At its deepest known point, the Challenger Deep, the seafloor plunges to roughly 1,035 meters, or nearly 7 miles straight down, deeper than Mount Everest is tall if you flipped the mountain upside down into the ocean. This is Earth's ultimate abyss, and tonight we're going to descend, layer by layer, into what makes it such an enigma. As we drop beneath the waves, the first thing to grasp is pressure. At the surface, the air around you presses with about 14.7 pounds per square inch. For every 10 meters you go down, the pressure grows by roughly one entire atmosphere. By the time you reach the bottom of the Mariana Trench, that force exceeds 16,000 pounds per square inch, more than 1,000 times what you feel at sea level. It's not just heavy, it's relentless, pushing in from every direction. If our bodies had air spaces like a balloon, they'd collapse long before we ever got close. Only carefully designed machines and creatures specially built by evolution can survive this squeeze. So how could anything live there? Life has a way of rewriting the rules. Picture a translucent fish with soft bones, jelly-like flesh, and skin almost without pigment. That's the Hadal snailfish, found at depths beyond 6,000 meters. Its body is tuned to the abyss. Genes that favor cartilage over rigid bone, membranes that stay flexible under pressure, and proteins stabilized by a special molecule called TMAO that helps keep them from buckling. Scientists have even sequenced snailfish genomes and found signs of pressure-tolerant cartilage and boosted protein stability, biology that seems engineered for a world of crushing force and cold. TMAO isn't just trivia, it hints at a hard limit. As fish live deeper, they tend to carry more of it, but that comes with a cost. At some point, their own tissues would become too salty relative to seawater to function. Lab and field data suggest teleost fish likely top out around 8,200 tassos and 8,400 meters, which is why we don't see fish right at the very bottom of the Challenger Deep. In fact, the deepest fish ever filmed so far, an ethereal snailfish, was recorded at about 8,136 meters in the Izu-Ogasawara Trench, while the deepest described species from the Mariana lives a bit shallower. Invertebrates, meanwhile, push even deeper. Tiny crustaceans and strange single-celled giants called xenophyophores dot the trench floor. Life threads the needle, but only so far. Food is scarce in the abyss. There's no sunlight, so photosynthesis can't help. Instead, life depends on what falls from above, flakes of marine snow, the occasional carcass, or on chemistry. In parts of the broader Mariana region where fluids bubble from the seafloor, microbes tap energy from chemical reactions rather than light, a strategy called chemosynthesis. These deep microbial communities can form the base of entire food webs, feeding amphipods, worms, and other specialists that have mastered the dark. It's a reminder that life doesn't require sunshine so much as it requires an energy source and the right chemistry. Now, how do we know any of this, given how few people have been there? Our story of exploration starts with rope and patience and ends with space-age engineering. The first crewed visit to Challenger Deep happened in 1960, when Jacques Piccard and Don Walsh rowed the bathyscaphe Trieste down more than 10,900 meters. Their dive proved a human-made vessel could survive the descent, even though a window cracked from the stress. Half a century later, in 2012, filmmaker and explorer James Cameron piloted the DEEPSEA Challenger solo to the bottom, spending hours filming and collecting samples. And in 2019, Victor Vescovo's titanium-hulled submersible, Limiting Factor, made multiple repeat dives, charting the seafloor in new detail and showing these feats can be done again and again. Together, these missions turned a single snapshot into a moving picture. The machines that help us see the trench are marvels. Remotely operated vehicles and autonomous landers carry lights, cameras, and sensors down the water column. CTD packages, clusters of instruments named for conductivity, temperature, and depth, ride along to measure the water's properties all the way to the seafloor. Their pressure sensors tell us exactly how deep we are, while added modules sniff out oxygen, pH, nutrients, and tiny particles. Data streams back up a cable or waits to be recovered, turning a silent descent into a scientific conversation. But the abyss doesn't forgive mistakes. In 2014, WHOI's uncrewed vehicle Nereus was lost during a deep dive, likely due to an implosion under the crushing pressure. An expensive reminder that everything about this environment is extreme. And yet the trench surprises us in ways that feel almost playful. When researchers lowered a special hydrophone to the bottom, they didn't find quiet. They found a soundscape alive with storms, far-off ship engines, and the calls of whales, an unexpected chorus echoing even 7 miles down. The deepest place on Earth isn't silent. It's connected to the noisy world above by sound that travels astonishing distances through water. Of course, the Mariana Trench is not just about extremes. It's about discoveries that change how we think about our planet. Each expedition reveals new species, slender fish and shrimp-like amphipods with odd biochemistry, and new ecosystems living on chemical energy alone. Some finds are bittersweet. In 2019, scientists reported microplastics inside amphipods from multiple trenches, including the Mariana, and earlier work found high levels of industrial pollutants like PCBs in trench animals. Even here, in a realm without sunlight, the fingerprints of human activity appear. The abyss turns out not to be beyond our reach after all. What's left to learn? A lot. We are still pinning down exact depths, mapping small valleys and scarps at the seafloor, and tracing how trench currents move food and larvae around. Big picture mapping is racing ahead too. As of mid-2025, only about 27% of the global ocean floor has been mapped to modern standards. The rest remains a patchwork. More than 2/3 of the seafloor is still waiting for its first clear portrait. The abyss may be the deepest mystery, but it's also part of a larger one. A planet whose surface is mostly water that we are only now truly charting. This isn't just curiosity for curiosity's sake. Trenches are born where tectonic plates collide and one slides beneath another. In the Marianas, the fast-moving Pacific plate dives under the Philippine Sea Plate, pulling the seafloor down and fueling a chain of volcanoes. Studying trenches helps us understand earthquakes, volcanoes, and how Earth recycles its crust and gases back into the deep interior. When we map and measure these zones, we're learning how the planet breathes. The trench also acts as a time machine and a model for alien oceans. On Saturn's moon Enceladus, the Cassini spacecraft found molecular hydrogen blasting from icy plumes, a clue that hot water reacts with rock at the seafloor, much like Earth's hydrothermal vents. Jupiter's moon. Europa likely hides a salty global ocean beneath an ice shell and may also host vent-like chemistry. By studying the Mariana Trench and other deep-sea sites, we're practicing for the day we can test for life in oceans far from home. The rules of chemosynthesis, pressure-proof biology, and energy sources don't stop at Earth's shoreline. With discovery comes responsibility. Parts of the U.S.-controlled region around the trench, including the Trench Unit and nearby volcanic and islands units, are protected as the Mariana Trench Marine National Monument, established in 2009 and guided by a management plan finalized in 2024. The rules curb commercial activity and set a framework for research and stewardship. Protecting a place like this means more than drawing lines on a map. It means limiting pollution, managing fishing where allowed, and ensuring that exploration leaves no scars. No lost cables, no careless debris, no shortcuts. The abyss may feel untouchable, but policies, permits, and careful planning keep it that way. If you think all this sounds simple, build a sub, go down, bring back samples. Consider the engineering ballet behind every descent. Materials must withstand 100 atmospheres. Electronics need housings that won't crack. Lights must cut through inky water without overheating. Even buoyancy becomes a puzzle. Syntactic foams and precise ballast drops control rise and fall. That's why repeatable dives by subs like Limiting Factor were a turning point. Not a stunt, but a sign the deep could become a working laboratory. It's also why we celebrate the explorers who go, and the scientists and engineers who make going possible. So where does this journey take us next? Expect smarter robots that can linger for months, pressure-retaining samplers that bring animals up without bursting them, and global mapping campaigns that fill the blanks between trenches and ridges. Expect surprises, new species with stranger biology, new chemical pathways that make life possible, and perhaps even new sounds in that deep, rolling ocean chorus. And expect more questions, because questions are the real payload of exploration. Each answer a door to 10 more mysteries. Here's the truth at the bottom of the world. The Mariana Trench isn't a void, it's a living edge. It challenges our bodies with pressure, our tools with engineering, and our minds with the possibility that life can flourish in places we once thought impossible. If we keep exploring with care, mapping wisely, sampling gently, sharing data openly, and protecting what we find, we'll keep rewriting what we know about Earth. And just maybe, that knowledge will be the key that lets us recognize life when we finally meet it somewhere beyond the blue.